So basically, as several of you or all of you know, there is a lot of push in science education to help students learn the practices of actual scientists. So scientists use models, scientists use language, and they use hands-on activities, experimentation, and how do we get these authentic science practices into the classroom? And basically, the curriculum that we have designed does incorporate a lot of the authentic science activities that scientists undertake. So one of the components is reading, writing, and communicating. And as many of us know, with the push towards hands-on activities in science, reading and writing kind of take a back seat, and there is often a neglect of text materials in the classroom. But with new genres of text, like electronic text in the form of hypertext and hypermedia systems, you can incorporate text as well as several multimedia devices that can be used to promote science education. So there are several strengths of electronic text as opposed to linear text. One of them is that they provide multiple links and interactivity. And something that students do when they build an artifact is they see the relationships between different science processes or concepts and principles. And electronic texts actually allow you to make those relationships more obvious to students. You can include visualizations and innovative representations in text, and by having students see the different relationships between concepts and principles, they allow for integration of science knowledge, which is an important goal in science education. Similarly, simulations are also a very helpful technology in enhancing science. And one of the strengths of simulations is that not to replace the hands-on activities that are so important, where students actually get the haptic feedback from their experiments and designs, but to actually explore variables that are impractical or impossible to explore with physical materials. So for example, what happens when there is zero friction? And now that's something that a simulation can be used to complement the actual design activities or the hands-on investigations that students undertake. They also allow you to combine multiple representations. So as students are working with the simulations, they can be shown a graph, or they can be shown different verbal, numerical, or pictorial explanations of what is going on in their virtual environment. And there is something to be said about the ease of setting up simulations in a classroom. We've been working with hands-on activities for several years, and you can only do a couple in a classroom period, or one or maximum of two in a classroom period of 45 minutes, whereas simulations allow you to test more, to run more test conditions, more trials. So students can easily change variables and see what the effect is on the science principles that they're learning. So that's another advantage of simulations. So basically my project, which is now in its 10th year, integrates multiple modes and multiple representations. So we have a hypertext system, CoMPASS, and design-based physical science units, and I'll show you the system as well as talk a little bit about the design activities in a minute. Students also use simulations to complement the design activities. So we are not replacing the hands-on activities with simulations, but where necessary, we have integrated simulations that allow students to explore variables that they may not be able to explore in their design activities. The whole curriculum is embedded in an inquiry approach. So there is, as you will see in the video clips, students brainstorm what they know and what they don't know. They generate questions that they can take to the hypertext system and find more information. They plan their experiments and investigations by thinking about what variables they can change, what variables are constant, and then they also collect a lot of data and justify and report their results. We do have professional development activities where teachers actually go through this curriculum in summer. And our teachers, the partner teachers, have been really our collaborators in the design and enactment and redesign of the curriculum through several years, both in Connecticut, where I was before I came to Wisconsin, as well as here. So let me talk to you a little bit about the hypertext system. The CoMPASS hypertext system actually integrates two different representations, concept maps and text descriptions. And the maps actually show the relations between science concepts and principles. And as I'll show you in a minute, the maps are dynamic and they zoom in and out, and in the form of a fisheye that actually shows students what concepts are related, most closely related to the ones that they are learning about. And students can also switch views between topics. And the simulations, again, allow students to test a few variables. Let me quickly show you what the system looks like. Okay. So one of our units is work and energy, simple machines unit. The other is forces and motion. And these are 6th, 7th, and 8th grade units that go from about 6 to 8 weeks in a regular classroom schedule. So once I click on simple machines, I get the two families of simple machines, levels and inclined plane family. And I can click on the inclined, oops, sorry. So I get some information about what the inclined plane family is, and I can then click on any of the machines, and I get a wheel map of the concepts that are relevant to understanding the inclined plane. However, it gets a little bit more interesting from here. If I click on work now, this is what I meant by the fisheye. The map shows work as the center, as the focus, because I clicked on work. And there is a description of work in an inclined plane on the right side of the screen. And the concepts that are in the first ring in the concept map are the ones that are most closely related to work. And the ones that are at the second level are related to the concepts at the first level. And there were a lot of design decisions and consultations with expert scientists, physicists, as well as teachers and students to figure out what level of detail you can show in the maps, because there's only so much that you can show on a computer screen. So we had to limit the number of concepts that based on what was relevant to 6th and 7th grade students. You can navigate through the text or the map. So for example, I clicked on distance now, and